Our next speaker is Chris Higgins. Chris is the Cecil and Salary Drinkard Professor of Structural Engineering at Oregon State University.
All right, thank you for the introduction. I'm going to talk about the use of a material that's not commonly used for civil engineering applications. I want to acknowledge my co-authors. These are my graduate students, many of whom have graduated at this point and are off in professional practice. Overview of this talk, I'll give you some introduction, some background information and the motivation for this work, present some laboratory test results from our full-scale specimens, including both shear strengthening as well as flexural strengthening, the first field implementation of applying titanium to strengthen existing bridge in Oregon, and then talk about a design guide that's been developed to help engineers be able to apply this, as well as a fairly new ASTM material specification, and then finally some conclusions. Kind of an overview, we have a lot of existing bridges built in the period of the 1950s and 60s during the Eisenhower Highway expansion, widely used throughout the country. And at the time, they were using newly standardized deformed reinforcing bars, right? State-of-the-art technology of the time, which allowed them to use higher bond stresses. And as a result, they could get away from using good detailing practice of anchoring those bars using hooks and bends. And so they used commonly used straight bar terminations where the material was no longer needed by calculation. They were trying to optimize materials at this stage of development rather than optimize construction. And at the same time, the design codes that were being used were not conservative, especially when it comes to shear calculation. They were overestimating what the concrete contribution to shear would be. And as a result, they were putting less stirrups in. As a result, we have a lot of bridges in the inventory that tend to exhibit some visual distress, including cracking, diagonal cracking, which tends to alarm most engineers. Or trying to extend the design life of these structures beyond their probably intended design life. And when we go and we apply modern design practices to evaluate capacity, we find that they're deficient. And as a result, we have to figure out what to do with them. We can replace them, we can limit the loads on them, or we can retrofit them. And retrofitting tends to be the most economical solution. All right, so there's lots of choices out there. Principally, people tend to go to carbon fiber as a choice. And if we look at kind of the material properties for carbon fiber, we find that it has high strength. If we just look at the carbon fiber, this is a pre-cured laminate bar. High strength, modulus elasticity about 20,000 KSI. But you can see it has very limited elongation, right? We're less than 2% elongation. It's elastic until it fractures, so we have no ductility. We've done a lot of work with carbon fiber, both surface bonded as well as pre-cured laminates, and this is a screenshot of a failure of a surface bonded carbon fiber sheet. And you can see all those white marks there are debonded regions within that beam as you're nearing capacity. And at the incident capacity, you're essentially rupturing the bond strength. And you can see in the picture there, the carbon fibers actually tearing off the surface, exploding off the surface. Prefer near surface mounting, and this is a technique whereby you cut into the skin of the concrete, not so deep that you're going to harm the internal steel, but you're cutting through the cover of the concrete and you're placing a reinforcing bar in that groove and you're using structural epoxy to bond that bar to the concrete substrate. When we've done this with pre-cured laminates, we will fail essentially the bond. And you can see that the upper left picture shows a carbon fiber bar that's kind of pulled away. It's still intact because the bond has failed. I think in all the specimens we ever tested with carbon fiber laminates, we only fractured one bar. Otherwise, you get bond failure instead. So you can't really make use of that very high strength material. When we have very tightly placed carbon fiber, that's the lower left picture, you don't get bond failure anymore. You actually rip the cover of the concrete off. And the interesting thing is that's a diagonal tension failure, but from the surface it looks like a vertical failure. The diagonal crack is actually hidden behind this intact skin of cover concrete that's anchored by the carbon fiber bars. All right, so with that background, what's the alternative, right? What's out there? And so what we were looking for is a material that's environmentally insensitive. It has high strength, but well-defined material properties, and it includes an efficient mechanical anchorage. And that's what leads us to titanium. Titanium, right? What in the world? No one uses titanium in structural engineering, right? It's simply too expensive. And it's really only applicable for things like aircraft and medical devices where we really are willing to spend the money to do it. And hopefully what I show you today is there's a reason to do it, and we can do it when it's still more economical than existing alternatives. So some background on the titanium bar. We're not just using pure titanium, it's a titanium alloy. It's so-called 6-4, which has 6% aluminum, 4% vanadium. Those are the alloying elements. If you look at a stress-strain plot, a Young's modulus, about 15,000 KSI, slightly smaller than that carbon fiber bar that I showed you before, about half that of steel. Yield stress, somewhere in the neighborhood of about 145 KSI for this particular bar. But if you look at the elongation here, you're getting 11% strain, right, at your ultimate, before you rupture the bar. And you can see at the bottom left, we've got the failed titanium bar's nice cup and cone ductile failure mechanism. So we've got this high strength, almost elastoplastic, perfect behavior with high elongation. So this is not your kind of camping titanium that you might have for your pots and pans. This is stuff that would be used by Airbus or Boeing, right? Aircraft fastener grade. It again has these well-defined high strength and ductile material properties. It has high fatigue resistance with a constant amplitude fatigue limit, about 75 KSI, with low notch sensitivity. It's impervious to chlorides. It really doesn't care about the salt. I always like to say when the world turns to dust, there will be these gleaming titanium bars shining in the sunlight with the cockroaches dancing on them. And the reason it doesn't care about chlorides is it forms a very stable oxide layer almost immediately. Coefficient of thermal expansion is actually better aligned to concrete than steel, and so we don't expect any thermal incompatibility or thermal stresses because of the coefficients. We can use conventional fabrication techniques, meaning we can shear it, we can cut it, we can bend it with what we would use with rebar. It's relatively lightweight, so handling it on the job site is fairly easy. It's about 1.7 times lighter than steel. And because it's a metallic, we can bend it, and we can fabricate a mechanical anchor inherently into that bar. All right, so some experimental work that kind of demonstrates what the material can do for you. All the work we do is at full scale. So we have replicas of vintage girders that reflect 1950s vintage practice, widely spaced stirrups, fairly low-grade steel. And we look at shear, we look at flexure. We have 3 or 10 different specimens that we've tested under shear, 3 of which are control. When we do shear, we use fairly small diameter bars, only 1/4-inch diameter titanium bars. When we do flexure, we've done 10 specimens, 3 controls again, and here we're using a 5/8-inch diameter bar. And we actually kind of tend to call it a number 5, like we would call it for a rebar. And we would call our 1/4-inch bar number 4. We've also done long-term durability studies where we look at combined fatigue and freeze-thaw. We've got a special environmental chamber built on a strong floor where we can test full-scale girders under these combined influence of mechanical loading and environmental exposure. And here we have 3 specimens, 2 in shear and 1 in flexure. Give you an idea of the size of our specimens. They're about 4 feet deep, 24 foot long, and each specimen weighs about 20,000 pounds. These would be typical of 1 girder line of a 4 girder line bridge. All right, epoxies. We've looked at 3 different types of epoxies. The bond strength is probably the most important parameter. They're all about 2,000 PSI or so. Turns out the one with the highest bond strength actually performs the worst. All right, so for shear strengthening, we're actually fabricating a stirrup, right? So because it's a metallic, we can produce bends. We're not just relying on the chemical bond along the epoxy. We actually get to have a mechanical bond with that hook anchorage. And so you can see the red highlighted titanium stirrup. Again, we're grooving that concrete surface. To get the hook into the core of the concrete, we're just hammer drilling a hole, and the tail of that bar is epoxied into the core of the concrete. We also have single leg stirrups shown on the lower right. The reason we have this inverted T is this is location in a negative moment region where you have high shear and high moment, which is the worst combination of those force effects. But we also have T specimens I'll show you next. So here's the installation. Essentially, we're grooving the concrete with a wet saw, like a skill saw you'd have in your garage, except it's lubricated by water, and it's got some special stuff so you don't shock yourself. There we're applying some epoxy, and we essentially, the titanium is flexible enough to spread the legs of that stirrup and snap it right into place, and it kind of holds itself in there because of those hooks. This is a picture of our inverted T in the freezer. We've got a hydraulic actuator that's dropped through the roof, which is bouncing it up and down to simulate truck traffic on top. The magnitude of the loads that we're applying are based on field tests we've done where we've measured the stress ranges in existing bridges in the stirrups. And we essentially are using Miner's rule to scale it up with about 2.4 million cycles with a stirrup stress range of about 13 KSI. And we can make the argument that that represents about 50 years of service life. At the same time, we're freezing and thawing this girder, and we're using about 120 cycles, and we've essentially calibrated that to our environmental conditions, the numbers of cycles we'd expect in Oregon, which would vary anywhere, depending on where in Oregon you are, from 25 years to 100 years of service life. It's like any place in the country, you have variability in terms of the numbers of freeze-thaw cycles that you might experience. All right, here's what our girder looks like after diagonal tension failure. The two pictures on the left are showing you that along that diagonal crack where we eventually have the failure plane, we're actually getting rupture of those titanium stirrups. So we're actually, because of the mechanical anchorage and combined with the bonding, the chemical bonding along the length, we're actually able to make use of that high-strength material. So we fracture the titanium. Here's some overall load deformation response. The green line that you see here is a control specimen. The red line is if we just look at testing the strength of that, we don't subject it to the environmental exposure combined with fatigue. And the blue one is if we first bounce it up and down the freezer 2.4 million times and we subject it to 120 cycles of freeze-thaw simultaneously, what we get is the same answer in terms of strength when we use this particular epoxy. And in fact, if you use good epoxy, you get the same result. If you use poor epoxy, the epoxy is the limit to this. I always make the argument, I don't really care who makes my concrete, I don't really care who makes my steel, but I do care about who makes my epoxy, because the first thing a contractor usually likes to do is replace the expensive epoxy that you specify with an inexpensive epoxy, and you do get what you pay for with epoxy. Here's a T-beam loaded in shear. First one, the green one, is the control specimen. The first test we did is the blue line. And you can see there's actually two lines. The red line and blue line are two separate specimens. The blue line fails in flexure. This is supposed to be a shear test. So we strengthen it for shear, and we essentially transform the failure mode to flexure. That's usually what you want to try to do. But as a researcher, when you're trying to investigate shear, you need shear failures to be able to compare shear results. And so the second specimen, that red one, was going to fail in flexure because it was following the exact same path. You can see how repeatable it is. That we saw for the first one. So what we did is shorten the shear span so we could increase the shear to moment ratio and actually get it to fail in shear. And shear is the wrong word, diagonal tension, right? Because it's a combination of shear and flexure. All right, so here's a flexural T-beam, and here what we're trying to do is fix those poor cutoff details, right? Where the designers in the 50s were just cutting those bars off in flexural tension regions without good detailing practice. And so we're trying to, for lack of a better word, use a non-contact lap splice and extend that cutoff location. Here's a T-beam, and you can see we're placing the titanium bars down near the soffit where the flexural tension steel is. Here's an inverted T, and in this case what we're trying to do is not have to do work on the top side of the deck, so we're trying to work from underneath. So we're applying the titanium bars to the soffit of the deck. We try to make this really hard on the girder. We actually cast in a piece of polycarbonate plate to represent the diagonal crack. So we've taken away any of your aggregate interlock in terms of the shear contribution of the concrete. All you get is dowel action in the compression zone as well as whatever you've got for stirrups. We do that because that allows us to know exactly what the equilibrium conditions are at the termination point of that crack. Here's some close-up details of the construction practice. There's some grooves on the upper right-hand side. At the end of the grooves, you can see that there's a hole that's hammer drilled into the core of the concrete to be able to anchor the hooks. We're using the same groove spacing and dimension requirements that ACI 440 would provide for carbon fiber bars. These are my graduate students actually doing the bending. You have to warm work the material to be able to do this. Titanium is a smart material. It color indicates for you. So you heat it with an oxyacetylene torch, and as you get it hotter, it starts to change color. When it turns that nice kind of golden straw color that you see in the lower left, you bend it, and that's our conventional rebar bender. To put the hook on. And you can do this in the field. So essentially, when you go to the field, one end has a hook already on it, and then you bend the hook wherever you need it in the field. So it's adaptable in that regard. On the lower right, I showed a furnace because we thought we needed to really precisely control the temperature, and we figured it was just easier in the end to use that oxyacetylene torch. So here's a flexural specimen. This is the control one. The little blue arrow, I wish I had an ability to show it to you, but on the bottom flange there, about halfway over, you see a blue arrow. That's where the bar is cut off. And if you look closely at the deck, you can see essentially that you've got splitting failure of the deck because that anchored bar was improperly anchored and essentially have a bond failure. When we apply the titanium, what we do is we transition it from, we essentially take away the defect, right? So there's the same location with that little triangle on the bottom flange, but now we produce a flexural failure where the titanium bars terminate, right? And that's essentially the core capacity of the specimen, as though all of that steel were well anchored. It's what you try to do for a retrofit case. And so here's kind of the low deformation response. We go from a non-ductile failure to a ductile failure. And again, we can predict the capacities pretty reasonably. Here's a T-beam. Again, we have this is the control specimen if we don't do anything. We have essentially a flexural tension failure where the anchor has pulled out. Here's the first case we did with this. We put a big hole in the beam so we could observe what was going on there. We took away a lot of the dowel contribution to shear strength. Remember, we've also taken away the contribution along the entire core by casting in that plastic. And as a result, we produced failure at the we shifted the failure load from what it was with the control, but it wasn't as good as what we would like. So we modified, we repeated this experiment with a smaller cutout observation point. And again, we transition it from a non-ductile shear failure to a ductile flexural failure. And there's the three responses. The blue is the control. That red one is the first one where we reduce the dowel contribution. And the yellow one is the beam where essentially we have beautiful ductile performance with that titanium essentially allowing the embedded steel to develop its full capacity and ductility. Again, we do the same thing, combining it with fatigue and freeze-thaw in our environmental chamber with the strong floor, bouncing up and down, 1.6 million cycles now for flexure. Again, representing about 50 years of service life. At the same time, we've got 120 freeze-thaw cycles to simulate, again, that range of service life for the environmental conditions. And again, they're being applied simultaneously. And then if we look at what happens, the control specimen shown in blue here, the red specimen is the specimen that we just test on the strong floor without environmental durability effects. And the blue one actually combines the environmental durability, bouncing up and down, freezing and thawing in the freezer, and then testing it to strength. And you can see that you get the same answer. Right, so we have a material, especially with good epoxy, that has very demonstrated good long-term performance. So here's our first application. This is the Mosier Overcrossing on I-84, which is our major east-west corridor. This small little overpass serves two quarries, and so it carries very heavy, short axle-based trucks. The inspectors noticed a very significant crack and vertical offset at a location. When we overlay the reinforcing cage with the observed crack locations, we can see that there's a very poor splice detail right where the beam transitions, the haunch transitions to a rectangular prismatic. And there's an indication of that critical zone where you have very small lap splice. Now, the designer at the time, if you look at dead load, you have negative moment at this region, but live load actually produces positive moment at this region. And our new trucks that we have are different than the ASHO trucks that would have been designed for at the time. So we're actually producing larger positive moments at this section. We essentially built and tested 3 girders, the as-built performance to see how close we were to having this existing structure fail. And then the designer's assumption was that, in fact, the specimen had failed in place, and ODOT actually used a shoring contract, emergency shoring contract, to hold that bridge up temporarily before they could repair it. And then if we just apply the titanium as it is without failing at first, right? So we failed one specimen and then applied the titanium. There's the details. It includes all the geometric variability of this girder, including cherry-picking steel to be able to best match the actual properties. So here's what happens if we look at the girder. It's a very quick test if we don't do anything. It's 2 load steps and it's toast. And in fact, if you look at the crack pattern, it looks very close to what they observed in the field. And that red curve shows you the capacity. The design capacity is shown by the black line, and the calculated demand is shown by the orange line. So by calculation, it wouldn't be able to carry the loads.
That's strain gauges on the inside. No, it's collaborative.
If we test the girder by failing it first, I will actually get the green line. If I apply the titanium without testing it first, I get the blue line. The stronger beam is actually if I fail the girder first and then apply the titanium. And the reason it's better is you get the steel out of the way, right? The steel is trying to do something and then it fails, and because it fails in bond, it essentially creates some damage to the concrete, which affects the bonding of the titanium. So if you fail the bond of the steel to start with, it gets out of the way and you just let the titanium do all the work, it gets better performance. The blue curve you see there, we went up to capacity, you fail the bond length, but then you still get to hang on by the hooks. And so that's why you drop way down, you increase the deformation because you have a now unbonded titanium bar, but it's still anchored at the hooks. So we unloaded it, reloaded it, and just relying on the hooks without the bond along the length, you can still see that our design strength is above the required capacity. So you get to wear a belt and suspenders. And this is what the bridge looks like after it was repaired. Now here comes to the cost, right? What they actually had a competing cost proposal for carbon fiber, and the titanium solution, even though nobody had ever done it before, was 30% less in terms of project cost than the carbon fiber alternative. So how to help you, there's a brand new ASTM specification out from Committee B10. It was approved in November. It's a standard specification for titanium alloy bars for near surface mounts and civil structures. Right? So it essentially lays out all the tensile properties, the chemical requirements, bond strength, cross-sectional areas, everything you'd need to specify it just like it's a reinforcing bar, except it's not reinforcing, like conventional rebar. There's a design guide available. It's written within the AASHTO LRFD format. It includes general conditions, materials, construction, installation, and design, both flexure and shear. And shear is for modified compression field theory like you're used to seeing in your AASHTO specification. It uses conventional analysis methods. It allows you to use your titanium alloy bar at yield. It includes environmental durability, not for the titanium, but for the epoxy that you might choose. There are 3 different limit states. It's actually more restrictive than carbon fiber, even though we're not asking the titanium to do anything more than what you're already allowing carbon fiber to do. It includes strength, service, and fatigue checks. The fatigue check is not for the titanium. If your titanium is going to fatigue, your steel is already gone. Right? So it's about checking whether your steel is adequate or not. And there's a comprehensive design guide to walk you through it for flexure and shear. So in conclusion, titanium alloy bars, we find that they provide well-defined material properties. They have high strength, they have ductility, they are environmentally durable, and because we can fabricate a mechanical hook inherent in the bar itself, we find that these are an economical solution for strengthening bridges and other structures. And I want to make sure I acknowledge the Oregon Department of Transportation. Bruce Johnson is our Chief Bridge Engineer, our technical advisory committees, and the research group that have helped us in conducting that research, as well as Perryman Company from Houston, Pennsylvania, who helped develop these titanium bars, and a whole bunch of undergraduate assistants.
So my question is, this is only for reinforced concrete application? Have this used for pre-stressed girders, or?
It's, yeah, good question. So the work that we have done is focused on conventionally reinforced concrete, but I think actually it has some distinct advantages if you wanted to apply it to pre-stress because of what you can do with the mechanical bending on it that you can't necessarily do with, let's say, a pre-cured carbon fiber laminate. So I think you could do it applied to pre-stressed as well, adapted to that. But we haven't done any specific research to demonstrate that.
Okay.
Great.
Thank you.
Yep, thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.